the previous lecture on SDN for IIoT, we looked at two things. First of all, we understood what is the SDN architecture, what are the different components of a generic SDN architecture, and thereafter we looked into the IIoT specific requirements and how SDN can integrate with IIoT and catering to these particular requirements of IIoT in a much more efficient manner. We continue further, and now we are going to look at few different solutions and applicability of SDN catering to different network scenarios in this particular lecture. So, if we are talking about SDIIoT, we have different types of networks. The traditional networks like your internet, public networks, sensor networks which is more specific to IIoT, and you also have this cloud, particularly industry grade cloud, industrial traditional bus networks connecting different sensors at the device layer and so on. So, how you are going to make them SDN enabled is what we are going to at a very high level look at, and particularly try to identify the main difficult areas in each of these architectures where SDN implementation will pose challenge and how you are going to do that to cater to these specific requirements. This is what we are going to look at in this particular lecture. So, first let us start with the sensor network. Sensor network, sensors etc. are key to IoT and IIoT. So, if we are talking about the virtualization, the software defined sensor network platforms, that means the existing sensor networks you want to make them software defined. If you want to do that, what you need to take care of is basically issues of number 1 sensor monitoring, number 2 data acquisition, and number 3 management and optimization of these sensors and sensor networks. So, typically you are going to have one view of a SDN or SD enabled sensor network like this. You are going to have at the very bottom the data plane. The data plane will have all these different sensors and so on. This is your data plane. Data plane has different sensors which may be interconnected through different access devices and so on, and these different devices in the data plane, the sensors etc. might be there in these different transportation devices, cars, buses and so on, or they might be there in the different industrial buildings or different other parts. So, this is your data plane. Then you have the control plane. This control plane basically has different components for sensor monitoring, data acquisition and management and optimization. Self optimization is very important in autonomous systems, and self optimization and self management overall has to be implemented in a software defined sensor network architecture. And on top, as before, we have all these different applications taking care of issues of utilization, fault tolerance, production planning, customized production, billing, business logic implementations and so on. So, all of these different applications over here. So, let us now focus on this particular control plane. So, we have to take care of issues of number 1 sensor monitoring, number 2 is data acquisition, and number 3 is this management and optimization, particularly from an autonomous management, autonomous optimization point of view. So, these 3 components, as you will notice shortly, will recur in different other network settings as well. Look at the internet, the public networks in general. So, public networks will consist of different components such as the switches, routers and access devices. So, these are the ones that will be there in the data plane. In the application layer, basically you have whatever we talked about earlier, that does not change more or less, but over here in the control plane, in the context of public networks, you have similar kind of things like the similar kind of issues like the ones that we discussed in the context of software defined sensor networks. So, here we are talking about again network monitoring, then data transmission service and management and optimization, particularly autonomous management and optimization. It is very similar to the ones that you had seen in the control layer for software defined sensor networks. In the context of industrial cloud, cloud as we have seen is very important. Data center and cloud, data center networks more specifically and cloud are very important for implementing software defined for implementing IIoT, and software defined IIoT for industrial cloud settings. You need to take care of issues like the ones over here in the control plane. So, here we have to take care of issues such as process unit monitoring, data processing service, and again this management and optimization stays the same like the ones before. So, processing and process unit monitoring, these are the ones that are there in addition to management and optimization in the control plane. These are the building blocks of the control plane in the industrial cloud, software defined industrial cloud in IIoT settings. If we are talking about industrial bus network, in an industrial bus network, what is going to happen at the device layer? You are going to have this industrial communication, the industrial bus, the communication bus to which these different sensors etc. are going to be fitted. Sensors and other network devices are going to be fitted to the industrial bus. So, this is your industrial bus network, and to which all these different machinery with different sensors etc. are going to be fitted. And as usual on top you have these applications, but this is very important. These are the different components specific to industrial bus network for the control plane in SDIIoT. So, you have over here bus state monitoring, data processing service, and third is the management and optimization. So, software defined networks for different settings, different architectures are all there. Lot of research work is going on catering to software defined networks of all different sorts, and more specifically for IoT and IIoT. IIoT industrial settings, industrial IoT requirements are more specific. There are certain specific requirements over here. So, there is a working group which is known as the 6 T's working group, 6 T's. So, this is basically TSCH. TSCH basically stands for time scheduled channel hopping. So, time scheduled channel hopping, here actually what they are talking about is channel hopping in a time slotted mechanism, where there are going to be time slices that are going to be there, and assigning these different time slices or time slots to the different devices and the controller at the same time. This is what this particular 60s software defined 60s basically talks about. This is a huge work that is going on. In a very nutshell, let me just give you the highlights, but if you need to know more beyond this, this is this particular literature that you can refer to. This is not the only one. There are so many different other literature talking about 60s, particularly software defined 60s. There are so many different research literature that are available for you to go through. So, in a time scheduled channel hopping TSCH scenario, we are talking about deterministic communication, which is very important in industrial settings. So, this deterministic communication will help in ensuring provisioning of resource allocation efficiently in constrained networks such as IoT and IIoT. Constrained because these are constrained with respect to energy, constrained with respect to computation, storage, network resources, and so on. So, there is this IETF 60s working group which introduced different objectives which are relevant for industrial process control, automation, and monitoring industrial applications. For implementation of SDN in 60s, there are different challenges. Challenges of dealing with unreliable links in IIoT scenarios. We have low power scenarios, low power network scenarios which are lossy, unreliable, and so on with respect to links and components and scenarios. So, it is a highly dynamic, unreliable, low power, highly constrained scenario where we have to implement SDN. So, this is a highly challenging job, and so many research efforts are being poured in order to do so. And here is this reference that you can look at to start with in order to understand how one could think of SDN implementation in 60s. So, control overhead is also there, because control overhead is there because you are talking about SDN. SDN, one of the important challenges is to deal with this overhead of control. Control overhead in SDN is a important challenge. It gives lot of benefits, but it is also a challenge, and how do you deal with this control overhead? For this, basically this slicing mechanism has been proposed, and in this particular slicing mechanism, what we are talking about is to have different time slices or time slots, similar kind of concepts like that, and have certain devices have certain time slots, the end devices, edge devices share certain time slots, the other time slots will be given to the controller. So, all of them will be using this the different time slices or time slots at different points of time and using them. So, so basically this slicing mechanism will give you dedicated forwarding paths across the 6-dish network in a much more efficient manner, and will also help you in reducing the control overhead. So, basically holistically one is going to have software defined 6-dish providing through the slicing mechanism, providing deterministic low latency communication for improving the performance of the network, particularly from a control overall reduction of control overhead and so on. So, the advantages would be that if you use SDN, you are going to take care of all of these things in a much more efficient manner. This is in a very nutshell, this is how this software defined 6-dish protocol stack looks like. So, I am not going to go through any of them in detail, but as you can see over here, these are these different layers. So, layers at the very bottom 802.15.4 standard that we have talked about earlier, but these customized ones like the TSCH RDC sync, then you have this 802.15.4 2015 TSCH MAC, and then you have this 6-LoWPAN HC. So, 6-LoWPAN basically, as you know that this is a network layer protocol, 6-LoWPAN, we have talked about it earlier in a different lecture, and this 6 basically from IPv6 comes and has been used in this 6-dish protocol. So, this name 6-dish basically this 6 comes from IPv6 or from the 6 of the 6-LoWPAN, and then you have this the concepts of the micro SDN, and this micro SDN basically introduces a lightweight protocol stack. It is a lightweight protocol stack that is capable of reducing the control plane overhead, and it is based on the IEEE 802.15.4 implementation in this Contiki operating system, which is for simulation of sensor networks. Contiki is widely used. So, this basically runs on top of the Contiki operating system. So, software defined edge for IIoT, this is the overall architecture. You have different industrial devices and equipments in the edge network like the ones that are shown over here, and then you have these different cluster heads, and you have these edge servers thereafter, which are going to be inter-networked in this particular manner, and then you have this SDN controller which is sitting on top in order to control the entire thing. So, you are going to have in the software defined edge IIoT architecture different components such as the cluster head, industrial cloud, edge network, software defined network controller, devices and equipments, and these applications which holistically has been shown in this particular architecture, and this is quite self explanatory. So, I do not need to go through each of these different components in further detail. So, software defined control plane is also applicable for smart energy, smart grid scenarios. In smart grid monitoring systems, one could be using the centralized controller. There are different other components in the software defined smart grid, components such as the distributed management system, the DMS, the DRMS, which is basically the distributed energy resource management system. The SCADA is there. SCADA is important for automation, as we have seen before, automation and enablement of software defined enablement of IIoT, and for SDIIoT as well, SCADA is a very important component for enabling whatever we have discussed. So, so basically this particular literature, in case you are interested for SDN enabled smart grid, this particular literature will give you the highlights of how you are going to deal with the software defined control plane for the smart grid. This is the holistic view of the software defined control plane for the smart grid. It shows only the control plane. So, you are going to have all of these different components including your southbound API, northbound API, and intermediate components such as switches and routers, operations and maintenance, service management, fault discovery, tracking, fault tolerance in general, security issues, topology management, and so on. So, all of these basically are taken care of in this particular layer, the control layer. And then you have on the other side, you have all these different components like the ones that I had shown you in the previous slide. So, SCADA, DERMS and DMS, these are part of this advanced distributed management system. So, so together basically they work hand in hand in order to offer the software defined SDN services for smart grid. So, the challenges with respect to SDN and its implementation in IIoT is IIoT, we are talking about a highly constrained lossy network having low power and so on. SDN implementation in this kind of constrained environment, for example, implementation of OpenFlow in this kind of constrained environment is required, but is a huge challenge. OpenFlow protocol itself is heavyweight, and implementing OpenFlow as such in IIoT constrained environments, lossy environments is a huge challenge, which is quite understandable, but it has to be done as well. So, there are consequently different works that are focusing on how you can make OpenFlow or other software defined solutions lightweight for implementation in these kind of constrained lossy environments of IIoT. So, there are different issues, different solutions. For example, consideration of fog architecture, where some part of the OpenFlow or the software defined solutions that you talk about can be implemented in the fog nodes, in the edge devices and so on, and the other parts can be implemented in the centralized manner in the cloud and so on. So, there are like fog enabled solutions that are also being proposed in order to take care of these different challenges of implementing software defined networks for these constrained and lossy environments of IIoT. We are now going to show you the implementation of OpenFlow through Mininet, which is a popular emulator that is there in the community. So, how you can use Mininet for implementing software defined networks and catering to the requirements of IIoT is what I am going to give you shortly a brief demo of. So, I have with me Mr. Samaresh Bera, who along with me will help me in giving this particular demo. So, I am going to show you first of all how this architecture that is going to look like for implementation in Mininet. So, let me just show you this thing first, that let us say that we want to implement the software defined networks in Mininet. So, Mininet is the emulator which with which we are going to emulate this software defined network scenario, and we are going to use the IIoT traffic more specifically. So, let us say that we have this Mininet which is going to take care of instantiation of these different nodes. Let us say that these round circles are your different switches. So, these are your switches, right, and these switches, let us say that we will have a scenario like this, that you are going to flow some IIoT traffic through these switches, and these switches will have something known as OpenV, which is basically open flow enablement in those switches. So, we have these open, these are all like the rounded circles are all these, let us assume that these are open V enabled switches, right. So, which implements the open flow in it, and we are going to have IIoT traffic coming through any of these different nodes, and then we will have a controller, right. So, in SDN we have already seen that we need some kind of a controller, and is the specific controller that we are going to use, its name is POX. So, POX controller we are going to use, and this POX controller is going to have this particular control over these different switches, which are these open V switches, right. And on top you have an application or different applications that might be running as well. So, let us say that some application is running. So, in our case I want to show you the execution of let us say some routing protocol. The simplest routing protocol that I can think of is the shortest path delay. That means that the shortest delay path is going to be chosen. So, in short this is known as SPD, the shortest path which has the path which has the least delay is going to be chosen. So, shortest path delay protocol is going to be executed using this particular controller. So, this is this scenario that we are going to show you now, how you are going to implement and how this routing is going to happen, and this is the Mininet environment which is executed over this Google Cloud, and I am going to show you how we are going to have this implementation done using Mininet emulator. So, before I do that, let me also show you something what you need to do before actually you run this these different requirements that we have. First of all, we need to ensure. So, first of all we need to, so for implementation first we need to basically have certain system settings. So, these are these different settings that will have to be done before we run our the shortest path delay protocol on Mininet. So, first of all these are the system requirements. So, you need to have Ubuntu 14 and above with a minimum 4 GB RAM with 2 core CPU and 20 GB storage. The other requirements are like you need to install a few software, Python 2.7, NetworkX 2.1 and PEEP, and few more installations will have to be done. Also after you have installed all of these, then you have to install the Mininet and the POX. These two software will have to be installed. So, Mininet installation, I have given you the source for downloading Mininet, and also for installation the command that can be used is also given over here. So, install.sh, right. So, this is going to install this Mininet, POX, etc., whatever other dependencies are there. So, everything is going to be installed after the downloading over here. So, thereafter we are going to have the network topology creation. For that this particular this particular package can be downloaded, and thereafter it can be installed. It can be installed in this manner. And for IoT traffic generator, this is this traffic generator that we have used. We have used the DITG traffic generator, and it can be it can be procured from this particular source. And for experiment settings, basically please go through our paper, which is the title of which is given over here. It was published in the IEEE Transactions on Emerging Topics in Computing in 2018, and the corresponding DOI is also given for you. So, using this particular reference you can go through our paper, the corresponding settings that are there. So, we will be using those settings for showing you this particular experiment. So, settings of the link bandwidth, link delay, flow requirements, traffic generation rate, packet size, etc., all of these are specified in this particular paper. So, use those settings. The experimental platform, as I told you, will be using the Google Cloud, and so this particular Google Cloud instance we are using. So, with the CPU Intel Skylake, 2 virtual CPUs, RAM 7.5 GB and 50 GB storage, and the forwarding principle will be using the shortest delay path. You could use any other routing algorithm as well, like your open shortest path first protocol or MRC, or any other routing information protocol, RIP, or whatever you want. So, for just example sake, we are going to show you the shortest delay path, and how it is going to forward the packets from one point to another. So, these packets are basically these routing traffic packets that we are talking about, and the results that we are going to show you are basically the ones which will take care of network performance monitoring with respect to throughput, delay, jitter. Jitter is basically the rate the rate of change of delay with respect to time. So, jitter, packet loss, these are some of the standard network performance monitoring parameters, and these will be used, plus for at the controller the packet in, that means the number of packets that are coming to the controller and the QoS violations that are there. So, all of these will be measured and will be shown. So, if you are talking about a research paper, then basically you plot these network parameters, you show how these network parameters vary with respect to time, and so this is the command that you are going to use in order to execute this particular protocol that we are going to show and its performance. So, this is this particular command that we are going to use. So, let us now go to this particular window, and let us show you how things are going to work.
Okay, so as Professor Mishra mentioned that we will be using the Mininet emulator to creating the network topology using Barabasi-Albert, and we will use the POX controller to control the switches. And we are using OpenFlow 1.1 as Mininet supports 1.1, it does not support 1.2 or 1.3. So, we will be using OpenFlow version 1.1. So, in this, in left side window we have the POX controller terminal, and in the right side we have the Mininet topology terminal. So, first we have to enable the POX controller so that it can listen to the switches. So, I will use some command. So, this is the command that we have written a code according to the requirements, like the shortest delay path. We will be running the Python, which is used to execute the Python program, Python, then pox.py, which will enable all the modules of POX controller. Then we have the design scheme, then OpenFlow.discovery, so that it can listen to all the switches whichever is being discovered. And finally, we have enabled the debugging method. So, let me run this command. So, you can see the OpenFlow is listening on port number 6633, and it is the local controller. So, that is why we do not have any external IP address. Now, the POX controller is listening. So, after enabling the POX controller, we will emulate the network using Mininet. So, for that we have the specific command, that sudo Python, then we have created a particular script to create the topology as well as to generate the traffic. So, after emulating the network, so we have created the network using Barabasi-Albert topology, and the POX controller listening to the switches. That's why you can see that OpenFlow.discovery discover different switches, the link detected, the switches detected. If I go up at the POX controller side, you will see that different links are detected, and these are the switches which are connected to the POX controller. Now, after creating the topology is stable and it is connected to the POX controller. Now, using the command gen, so I will generate the traffic. Okay, so after writing gen, so it means it is enabling to generate the IoT traffic which we have defined at the which have written in the script. So if I press on gen, then it is going to generate the IoT traffics. Okay, so we have emulated the traffic for 100 seconds. So that means for 100 seconds it will generate few number of flows. So a flow is a stream of packets. That means we are generating few number of flows, but number of packets are in the order of 1000. So you can, in the left hand side at the POX controller, you can see packeting for UDP flows, packeting for TCP flow. So different packet flows are generated, and the POX controller receives the packeting messages. So just let us wait for some time to complete the experiment. Then we will show you the results. Yes, so all the traffics are generated, flows are generated, and you can see the finish on UDP port. The different ports are generated to as source. So we have completed the traffic generation. So let us quit the Mininet emulator. So in the left hand side, you can see at the POX controller, it is detected that the switches are disconnected. So disconnected with the switch ID number. Now let us show you the results. So here you can see at the Mininet emulator, a log is generated which contains the different network performance metrics. So let me decode it. So as we have generated the traffic using DITG generator, so we have to use this command ITG decode. So the command is ITG DEC, then the log file name. So it is just compiling the entire thing. Now at the end you can see, so we have generated the total number of flows, which is 24. Total time is 50 seconds. So although we have defined 100 seconds, within 50 seconds all flows are generated and routed in the network. And as I have mentioned, the total number of packets is in the order of 1000. So for 24 flows, the total number of packets are generated 74,150. And we can see different things like what is the average delay. This is the average delay, that is 218 millisecond. Then average jitter, which is 18 millisecond. And then we have the average bit rate, which is the throughput. So we have got 4578 kbps. And finally at the end you can see average number of packets dropped, which is 1.85%, which is very minimal. So you can design your own benchmark and you can experiment it. So and accordingly you can measure the network performance. At the POX controller, let us see what happens. So I am exiting the POX controller. So where we have stored the results, let us see what we have obtained. So stats1.log. So we have generated this one. So let me check what we have got here. So total number of IP packeting we have received 277. So number of UDP packeting we have received 202, because typically, as Professor Mr. mentioned, that typically in IoT scenario we have UDP flows. So that's why we have counted the UDP packeting also. And number of UDP flows is 24. So in the right hand side you can see the number of flows is also generated, which is 24. Number of QoS violated UDP flow, which is 0. Okay, so although we have 74,150 packets in the network, but we have got only 277 packeting messages at the controller end. That means according to the flow rules, multiple number of packets which are matched with the flow rule eventually forwarded to the destination without generating the packeting at the controller end. So this is a small demo we have shown to you so that you can emulate IoT traffic and you can monitor the network performance. Also, you can fetch the real data which are coming from the sensors to the network, and you can deploy your own routing algorithm using the SDN controller in the real time to have, let us say, minimized delay or minimum loss, or let us say that we want to have the maximize the network efficiency. Okay,
so with this we come to an end, and this is a list of different references for you to go through further on IIoT and software defined IIoT. These references will give you better idea about the different solutions and the different initiatives that are in place. This particular literature I would encourage you to go through in order to understand the 6TiSCH architecture and its adoption for industrial IoT scenarios, and how you could have the SDN enabled for this 6TiSCH architecture for IIoT. So, with this we come to an end of the entire lectures on software defined networks for IIoT. Thank you.